Hi, my name is Philipp Freese. I'm a postdoc in Hamburg, and I'm going to talk about super resolution in parallel and in time integration to accelerate simulations with the ICANN. A lot of words, at least there's a bit on super resolution, which is like the ML part, and I think most of you are probably interested in that. I am actually more involved in the second part, namely the parallel and time integration, and I hope to capture at least the main ideas of both of these parts, okay? So my work is within the so-called ExaOcean project. So we are trying to accelerate simulations with the ICANN code. And what you see here is a simulation of the North Atlantic. It's a so-called sub-mesoscale telescope. So we have a telescope that the grid within the North Atlantic is of a resolution like below 600 meters. So you actually can resolve something that is below 1 kilometer, so sub-mesoscale. And actually, the importance of this is, of course, that we all know that like microscopic effects can or have an influence on macroscopic behavior of our flow. And this is exactly what you want to see, right? You want to capture the microscopic effects to really model the ocean. And just to give you a feeling, like this is the North Atlantic. There we are sub-mesoscale resolving, but on the other side of the Earth, we would have a grid that is like of size of 12 to 15 kilometers. So very, very coarse. And the point is you can already do these simulations. I mean, you see the picture, of course, but it's not really feasible to do that for climatologically relevant timescales. And the goal of our project is really to accelerate like simulations like this SMT. So a very few words on ICANN. So ICANN is the so-called icosahedral non-hydrostatic weather and climate model. It's an operational code developed by many partners. For instance, the Max Planck Institute for Meteorology and the German Weather Service. And these are also collaborators within our project. It is operational, so it is used actually to do forecasting. I want to emphasize it is already like a bit of legacy code. It's Fortran, so it took me quite some time to get into the code. And in particular, the ocean component, so ICANN is a bit special. It is not really involved in the actual forecasting. It's like, yeah, its own little business, I would say. Nevertheless, the goal is, as I mentioned, to somehow accelerate the simulation that we can do with ICANN, okay? So we are not there yet, so we cannot yet simulate the full SMT. What we actually did so far is to consider the so-called Galevsky test case. So I would say, as usual in science, you go back to something that you can handle. And this is actually rather boring, you could say. So this is just shallow water, so 2D. We consider this so-called Galevsky test case. I come to that in a second. So shallow water equation basically couples the velocities. So now only the two-dimensional velocity is v to the sea surface height, eta, okay? And this is, of course, a nonlinear PDE. So I'm actually a mathematician, so I just see a PDE and I don't know, I don't care about any of the physics parameters at that point, okay? So therefore, I have my collaborators. And the Galevsky test case is like an interesting test case because you start with this condition here, and actually this, what you see here is like a jet on the northern hemisphere. And this is a stable configuration, but you insert a small perturbation. And this is already after 24 hours. If you continue to 3 days, you already see a small wiggle. And then after day 6, like the instability hits. And yeah, well, you get something that looks turbulent, I guess. Well, and the point is that this is really this is really depending on the mesh, okay? If you have a coarser mesh, this instability will hit earlier. And this is some kind of an effect that you want to capture right, okay? You want to capture this onset at the right time. Okay, now the first part, machine learning. And I want to emphasize once again, I'm not the machine learning expert in our project. Still, the results are already promising, I would say, so I present them here. And we call this dynamic super resolution. And the idea that we have is basically we still use like the numeric time integration within ICANN. So we somehow evolve from time step t to t plus delta t. And this is done with ICANN with a classical time integration scheme that is in there. And then from time to time, we like use a machine learning model, and this time is delta C, so the correction time, and this is way bigger than the time step delta T, okay? So to give you a feeling, delta T in the experiments that you see is 10 seconds, whereas delta C is 12 hours. So this is really just very infrequent corrections. Well, and then we just, I mean, of course, we trained this model with like pairs of coarse and fine resolution data that have been evolved simultaneously, basically, and then we can calculate the error. And this is basically how we train our model, and then we simply correct our solution and we feed this solution back in our time integration, okay? So we really do a hard replacement of our solution. Okay, and here are the results. And first of all, take a look at the top left. So this is somehow the reference, 2.5 kilometer grid. And then you see below that, so middle left is 20 kilometers, and you can definitely see that you have already in the 20 kilometers, you have like an onset of this instability in the middle region, which is not there in the 2.5 kilometer region, right? And then we have like an intermediate solution, the 10 kilometer, and then in the middle right, you see what happens if you have a 20 kilometer resolution and do this ML correction every 12 hours. And well, I mean, you see there are still some artifacts here, but in general, the region here is flattened, at least compared to the 20 kilometer computation, okay? And this is definitely seen in this error plot on the bottom, where we have the difference of the ML correction and the 20 kilometer one to the reference solution. So this is basically, I mean, I would say this is in the eyeball norm, this looks good, okay? This is somehow what you can see. And of course, you can also have a look in errors and errors over time. So in these plots on the left, the x-axis should be time in days. So usually we compute for 7 days. And then you have, I hope you can see that, you have the dotted line and the dashed line. So the dotted line is the 20 kilometer one, the dashed line, the 10 kilometers, and the blue line. So that one is our ML correction. And you see that we are always below the 20 kilometer simulation, okay? And this is somehow, well, what we want to achieve in the end. So somehow we can use a 20 kilometer coarse grid, do the ML correction, and be like almost as good as a 10 kilometer resolution. And this is somehow, well, the first results that we have. Of course, we, at the moment, we are moving to the full ocean model. So there things might look different, but this is at least promising. And then on the right, I just wrote some preliminary numbers. So I want to emphasize this has all been done on CPUs and actually no parallelization in the ML model. So these numbers will get definitely better. But we are already better, like the 10 kilometer in concerning time. So there is already a speed up without, in parentheses, in quotation marks, without losing accuracy, okay? So this is somehow the dynamic super resolution approach that, that we took, okay? Well, so, and I want to emphasize all this is in a preprint by us, and the main one who did all the machine learning was Maximilian Witte from DKRZ. Okay, and now I want to move to the second part, which is like on the other side. So the machine learning is meant to improve somehow the spatial resolution problem, namely that we can now compute on coarser grids and still effectively capture what is happening on the fine grid, which is basically done by our machine learning model. And now on the same, on the other hand, basically, we try to improve like the time integration, okay? And this is done with so-called parallel spectral defect corrections. I could probably give a complete talk on that, but there's not much time, of course. This is actually what I'm working on mostly, and I try to keep the formulas as brief as possible. I don't know if there's any mathematician in the room, then we can talk about this way longer, probably. Still, what we are doing is we start with some kind of generic ODE on the top left, where f is, of course, now something like a nonlinear function. And I have, of course, like at least the shallow water equation in mind. And what you usually do is, of course, you can transform, or you want to solve this on some kind of a time interval from 0 to delta t. And what you usually do or can do is to write this in some kind of a collocation problem. And if you could, or if you want to do that, you could solve this, but this is horribly expensive because you have to invert this matrix Q, which you do not want to do. And then there was an idea around the 2000 to like rewrite this in an iterative way, okay? So, and this is exactly what SDC, so spectral deferred corrections, is doing, is basically you iteratively solve for UK, okay? So, and the point is that you really repeat this within one time step. And each time you repeat this, you increase the order of your time integration scheme by 1. And this is pretty neat. So in the end, you can start with a very easy time integration scheme, you iterate, and then you can end up with high order time integration schemes that give you good stability and accuracy, okay? In general, this works with Q delta. So this is now like the preconditioner being like just a lower triangular matrix. This is what SDC started with. And if you like write down a pseudocode, I don't want to go into detail here. What you basically have is that within one of your so-called sweeps, you have some kind of nodes, and all these nodes would always depend on the values on the previous node. So there's no way to somehow parallelize anything. And then, like in 2018, Robert Speck actually from Jülich, I think was the first to write this down, had the idea to like replace Q delta, like the lower triangular matrix, with the diagonal one, and the diagonal matrix then enables basically parallelism across like one sweep or within one sweep. And this is somehow what we did. Okay, so we used OpenMP within there to speed up our time integration scheme. Okay, and just to give you yet again a very brief picture, usually you want to evolve from Tn to Tn+1, and now we introduce some kind of sub-steps. This is what you do with SDC, and due to this diagonal structure, you can now compute all these sub-steps in parallel. And as I mentioned, you not only do this once, but for instance twice, then you have a second order scheme. So you need these values from the first sweep in the second one, but then yet again, you can do all this in parallel. So this is a very small scale parallelism. Well, so basically, that's the main idea of parallel SDC. So you get a high order method, but in general, you only have very few sub-steps, okay? So in practice, what we are using is 4 sub-steps. So you only have very small parallelism available, okay? But actually, this is exactly what we want, because ICANN itself is already, I would say, highly scalable. So it already uses like a hybrid MPI OpenMP parallelization, or I mean, most of ICANN is nowadays already ported to GPUs. So our goal when this project started was really to just add a little bit more parallelism to this time integration method, okay? And just to give you the actual configuration, so we are using 4 nodes and 4 sweeps. So in the end, we have like a 4th order method, and the like established method in the ICANN is actually a 1st order scheme. So I mean, we beat that right away. So this is, you will see that pretty pronounced. What is really difficult is that ICANN is like already, well, a horribly understandable code from my point of view, and to actually implement this additional parallelism in ICANN is not a fun task. And in particular, as there is already this hybrid parallelism, it is not easy at all to add another level of OpenMP in there. I mean, in principle, you would think, okay, this is just nested OpenMP now, but it is not, because actually what we have to do is we have to do the MPI calls within the outer OpenMP loop, and this is, well, not nice. I mean, I still not managed to implement this in ICANN, okay? I managed to implement this in like toy examples, but it's not easy to do that in ICANN. Therefore, all what you see in the following is like only on one node of the Joules cluster. And this just uses nested OpenMP now, okay? Still, what we can get is quite some nice speed up. So what you see here is the blue line with the crosses is the so-called Adams-Bashforth scheme. So this is actually the first order method that has been an icon, or an icon O, I have to say. And you can also see there was already like an OpenMP parallelization in icon, okay? And this is exactly what you see. So if you take this Adams-Bashforth scheme with 2 threads as your baseline, basically you see, okay, you can get a speed up of 4 compared to that one if you invest more and more threads. And then you see this parallel SDC, which is actually now nested OpenMP. So we have OpenMP in the time loop and OpenMP in the like intrinsic icon space parallelism. Then you see, okay, you directly get a speed up of over 2. If you basically what we do there is we just invest all the OpenMP parallelism in time now, okay? And then compared to this Adams-Bashforth with 2 threads, we can get a speed up of about 12, which is quite nice. So, well, this is at least what we got so far, and I want to emphasize these methods now use time steps such that the accuracy of both is identical or almost identical. Okay, and then I want to basically finish with this work precision plot where you have like the time on the x-axis and the error on the y-axis. And what you can see here is in orange, yet again, this parallel SDC, and then in blue, this Adams-Bashforth. And what really drives me crazy a little bit is this small blue dot on the left, because this one is the only dot that where Adams-Bashforth would still be like faster than SDC. You cannot go further to the left. So this is the time step, the last time step. That is still stable. So, but well, you see, if you are interested in an error of 5%, well, you should still use Adams-Bashforth. I'm confident that we will beat that eventually, but so far we cannot. But so this is exactly what you now see, that if you are interested in higher order, just in higher accuracy, just due to the higher order of your parallel SDC, you will directly win with that method, okay? Okay, so I think with that, I will wrap things up. So what I presented was like, were like 2 approaches. On the one hand, this very brief topic of super resolution to enhance like coarse scale simulation. Well, so, and I want to emphasize this has been in 2D. We are just working on the 3D case now. And then the other part was like this parallel in time approach to accelerate icon further in this time integration, which is really meant as a small scale parallel in time method. And of course, the future research, I touched, I think, basically on all of this is yet again written down here, and all of this has been funded in this ExaOcean project. So I think with that, I'm at the end of my talk. So thank you for your attention, and I'm happy to take questions.